Solve the exponential equation using logs. We're going to do it first with logs, and then we're going to do it with graphical methods. So here you have your problem, and the base on the right side, which is 5, doesn't match up with the base on the left, which is 2, and it can't be made to match up. Like if this side was 8 over here, it's really base 2 because it's 2 to the third, and then you could do it by hand. But because it's not matched up, we got to use logs on both sides. So we're going to take the log base 10 of both sides. So we're going to have this. That's all we did, log base 10. So if these two are equal, then log of this equals log of this, because these two inside parts are equal. Then we're going to use the power rule. Here's the exponent. You're going to bring that whole thing down. You can't bring parts of it down. You're going to do the whole thing, and that's down in the front. And so it's down in the front of log of 2 equals, and this is just carried down. Then we're going to solve this. We're going to divide both sides by log 2. It comes down underneath here and knocks off of that left side. So now you have this. Now we're going to add 4 to both sides. So the 4 adds over. You can put it in front or the back, doesn't matter. Then divide through by 3. Well, really we're thinking multiply by 1/3. The whole thing like that. Divide by 3, same thing as multiply by 1/3. It knocks off here till you just get x. And then this is 4/3 plus 1/3 of this fraction. And then we just multiplied the 3 in the bottom there and got this. Now that's what's called the exact answer. If they ask for the exact answer, that's what x is. But if they ask for a decimal answer, then you execute this in the calculator, and you're going to get, as we can see right there, it didn't fit all on the calculator page, but anyway, we're going to get it to 2.1073, which is this. Okay, and then graphically, you put the function on the left in, the number on the right, choose a decent window to be able to see the intersection, do a second calc intersect, as we've done millions of times, second calc intersect, and gives you this point right there, which is the same number as we did by hand. So you're going to be asked to be doing it by hand and with the calculator method. You always got to know both. Okay, now we're going to go on to example 2. Example 2 is showing how to solve an exponential equation that's more from an application. So here's the application. We've done something like this before. Radiation at a test site decaying. So it's decay rate, 2% per year. There was 2,000 millirems of radiation present at the site in 1960. Humans can handle 440 millirems of radiation. In what year, the date, will it be safe to return to the test site? Okay, so the function that would be set up was 2,000 is the initial amount. It's decaying at 2% per year. That's decay rate. So it's 0.98 is the decay factor. And so basically you want to know when this function reaches 440. What is the time? So divide both sides by 2,000. And you could leave this fraction, but it's begging to be reduced. So we reduce it. I did that over here on the side. Reduce down to 1150. Makes it just a little easier. Equals 0.98 to the t. Then you take the log base 10 of both sides. The power rule works on this one. The t comes down in the front, so you get this. Then you divide both sides by log of 0.98. That's why it comes downward in the bottom. And t equals this, and then I just turned it around. There's a t. That's the exact value right there. Exact. But if they want a decimal, then you just put that in the calculator. It didn't show it all, but you put that in the calculator and you enter and you get this. So about 75 years after 1960, that's the year 2035, the test area will be safe. Let's just verify that with the calculator method. Put the function in. Here's the goal, 440. Figure out a window. It has to be at least a 2000 in the y, so I went to 2200. And you don't have to mess around with the x max to see when you can finally see the intersection. Then when you do a second calc intersect again, second calc intersect, then you'll find this point, which is the same exact number as we had with this one. So this one matches up with this, and so we know we're correct.